Welcome everyone to our technical series of webinars. Today's topic is Cryptography-Enabled Data Science, meeting the demands of the data-driven enterprise. Today you will be hearing from Duality's Vice President of Data Science, Dr. Marcelo Blatt, and Duality's VP of Strategy, Ronen Cohen. Dr. Marcelo Blatt leads the data science team at Duality. Previously, he was Director of Data Science at Cisco and led the data analytics team of EMC at RSA. Marcelo holds a PhD in physics from the Weizmann Institute of Science. Ronen Cohen leads strategy at Duality, helping clients leverage privacy-preserving data collaboration solutions. Previously, he was the Director of Product Marketing at Dataviner, leading the product marketing function globally across all private and public sector verticals. Ronen also spent several years in the fintech and regtech spaces at Intralinks and NICE Actimize, as well as building his own personal lending company. Now I will hand it over to Ronen to get us started. Ronen?
Thanks, Lucy, for that introduction. I'd like to start with just a very quick overview to orient you about the space we're talking about. I'll move to a case study that will serve as a guidepost for us for our discussion, and then talk about the underlying technology. So Duality, as Lucy said, is a privacy technology company, and we enable organizations to collaborate with one another in a privacy protected, secure, and regulatory compliant manner. We combine data science with security and with privacy enhancing technologies like homomorphic encryption, multi-party computation, federated learning, and more. Basically, you can join, link, and enrich sensitive data sets from a variety of different sources and operate and analyze on them while ensuring that privacy is protected at all times. If we can please go forward, Marcelo. For today, I wanted to walk you through a short case study of how this technology is used before we really dive under the hood. And the example that we'll use is a medical analysis that was conducted by Harvard Medical School and Dana-Farber Cancer Institute. In the healthcare space, it is very challenging to get really good data and really good insights because of privacy and regulatory concerns. And at Harvard and Dana-Farber Cancer Institute, researchers were looking for a way to find correlations between DNA and genes with cancer outcomes. Basically asking the question of what is the correlation between this gene and this type of cancer? And does that mean that you have a predisposition? Does that mean that you are immune? Does that mean that certain types of treatments will or won't work? This is very, very challenging to do and very time consuming given HIPAA laws and other types of privacy concerns. And so Duality was used to encrypt different disparate data sets from multiple healthcare providers, link it together, and analyze it in aggregate without ever decrypting it. And what Harvard and Dana-Farber's researchers found is that they were able to analyze the genetic data and cancer data of hundreds of thousands of individuals 30 times faster than any other privacy protecting method or technology. And so what this means at a high level is that researchers and pharmaceutical companies and healthcare providers can make decisions faster, create treatments faster, and provide better overall care. And this is only possible while preserving privacy. And so if we can go forward, thank you. This specific project was in particular enabled by a specific type of privacy tool called homomorphic encryption. If you've heard of encryption before, you've probably heard of encryption at rest or encryption in transit. You can think of homomorphic encryption as encryption in use. What it allows you to do is to take different disparate sensitive data sets, encrypt them, and analyze them without ever decrypting it. So it's really end-to-end encryption as it is meant to be. One can apply data science and other analytics to homomorphically encrypted data and still get the exact same results as if they were operating in the clear without ever seeing the underlying data. Again, this is incredibly secure. It is open source. It is standardized encryption, and so it is very safe to use. But at the same time, it sounds like totally black magic. How can one encrypt data and still analyze it. And so for that, I'd love to turn it over to Marcelo to explain how this is even doable.
So really, many people ask how it's possible that you have, from one side, encrypted data, and for the other, you can make a computation. So I would like to provide you an example and an explanation of how this is possible without using too much math. So first, we have to talk a little bit about how we encrypt the data, and then with this particular encryption, how we are able to make computations. So a lattice-based, a homomorphic encryption is based on lattice-based cryptography. And I choose one of the earliest works on this field, which is called GGH, given that Oded Goldreich, Shafi Goldwasser, and Shaya Levy invented it. And it is not really the one that is used today, but it is close enough and still is much simpler to explain and provide you a real intuition without too much mathematics. So to start with, let's start by defining which is a grid. A grid is a lattice is a set of regularly spaced points in the space. This is an example of a grid in 2 dimensions. Then a vector is just a point in this grid. The next thing that you have to know is a basis. A basis are a set of vectors that enables you to generate this grid. Now, a point in the space can be represented by a linear combination of the bases. If you restrict these coordinates to be integer numbers, you get a point in the grid. Now, as any cryptographic system, it is based on a hard mathematical problem to solve. For instance, RSA relies on the fact that factorizing numbers is hard. In this case, we are relying on what is called the closest vector problem. That it states the following: if you have two bases, which is a bad one in the sense that the vectors are far from being orthogonal, then if given a random point in the which is outside the grid, it is very hard to find the closest point in the grid. Of course, that at the beginning, at first glance, you will think that it is easy, but in fact, you can convince yourself that it is not, and in particular, when we are working in very high dimensions, the typical dimensions that we use are ranging from 8,000 to more than 100,000 dimensions. So the idea is for encrypting is that, let's say that you are willing to encrypt a list of numbers, of integer numbers, so you can find set the corresponding point in the grid and adding noise to it. And then, as I said, given that the closest vector problem is a hard one to solve, it will be very hard to you to go back and understand which was the closest point. Now, if this is encryption, how we should decrypt that, right? So let me explain you. We have a ciphertext. Then the basis is known for everyone. Now, as you know, every encryption system also is based on a secret. In the case of RSA, the one that is performing the decryption also knows one of the factors of the decomposition. In this case, the secret is a good base of this lattice. So if you have a good base, finding the closest point turned out to be an easy problem to solve. So the decryption will be just finding the closest point given the good basis, the one that it is almost orthonormal. So if we go to the classical 3-step of a crypto system, The key generation in this case is simply given a lattice generating a good basis of the lattice that we will call A and a bad basis that we will call B. So B is going to be the public key known to everyone, while the A is going to be kept secret. So how we do the encryption, as we mentioned before, given the set of numbers that we are willing to encrypt, we will only simply adding noise. So this will be our ciphertext. For the decryption, we once we get the encrypted the ciphertext expressed in the bad basis, we transform it to the good basis, and then we use what it is known as a Babay's algorithm to find the closest vector. So this is as simple as that. Now the next step is, okay, how we do computations over encrypted data. So let me walk you through this process. We start by, let's say, 2 plain texts, right? We encrypt them. And in order to encrypt them, we need the basis that we were mentioning before. So we make the encryption just by adding noise. Then we make the vector summation of them. This is a vector, right? And now the question is how this vector relates to the decryption of this vector, or the decryption of this ciphertext relates to the original plain text. So as we mentioned before, in order to decrypt, we have to know the good basis. We express the ciphertext in the new basis. With this information, we are able to find the closest point. Then we got this the plain text, right? Now, if we recall the original plain text, we see that simply it is the element-wise, the addition of the element-wise of each one of the components. And then in a similar way, we can have the element-wise of the multiplications, the inner product. We can have also element-wise evaluation of polynomials, because polynomial is just multiplications and summations. And in particular, there is we have a strong support on Chebyshev polynomials because there are special ones, and on matrix arithmetics. Now, just to finish and close this, let me mention that there are different schemes in homomorphic encryption, BGB and BFB, that are used to make computations on integers. CKK-S, which is used for fixed point float pointing computations, and FEW and TFHE, which are used for Boolean computation. And it is important to remember that the encryption scheme which is used in this homomorphic encryption is what is known as a ring learning with errors from Revit.
Thanks, Marcelo. That's really interesting. And I think you made it easy to understand even for a non-PhD. I'd like to focus in on a specific family of computations that we're asked about a lot, and that's machine learning. So you spoke in general about how is it even possible to compute and analyze encrypted data, but are there any nuances or any differences when you're looking at machine learning models specifically versus other types?
Okay, regarding machine learning, there are basically 2 main ways of using homomorphic encryption. One, it is known as the transpiler approach, which is converting C++ code into Boolean circuits and use the FEW or TFHE to emulate these circuits. Now, this is a very promising direction. It is very flexible. It is very general. And the problem is that today performance is not so good, and therefore it's more in a research stage, I would say. Palisade support this, and we are working with companies in this direction. There is another way, which is a little more involving, which is to craft again the algorithms in such a way of making them homomorphic encryption friendly. And rather than talking in general, let me show you a particular example. Let's look to the decision tree case. The decision tree, as you know, relies very heavily in the fact that we have if-else statements. And if the if-else statement, even though in the clear is very easy to implement, it is very hard to be implemented in homomorphic encryption. So rather of computing complicated functions, we have to find an alternative way of formulating this problem. And it turned out that a decision tree can be written as a polynomial. And as we mentioned before, a polynomial is very friendly because you have only multiplications and summations. And even more than that, we have, it is possible to write this in an automatic way using a recurrence formulation. So in this way, you are getting the same result in a different formulation, but in a very high performance.
Okay, so thanks everyone for submitting some chat questions. We're running close to the end of the webinar, but I think we have time to squeeze one in. The first question is, do you need to be a data scientist or cryptographer to use your platform?
As from my perspective, you don't need to be a cryptographer. You basically need to I mean, I am myself a data scientist. I think that data science is good enough, in particular, if you have knowledge about linear algebra, which is the basic mathematics behind the cryptographic lattice.
From my perspective, you know, it depends. We have an application layer on top of our cryptography and on top of our data science. And so many of the use cases that we focus on are have nothing to do with math, if you will, at least to an end user. For example, we didn't cover this use case, but we do a lot of work in financial crimes and enabling banks, as an example, to share information with one another. And the users there are money laundering investigators or fraud investigators or detectives. These are not people that have a background in math typically or in cryptography. And so I think to Marcelo's point, it depends on what you're trying to do. Obviously, if you're trying to look for correlations between DNA and cancer and you're doing different types of analytics, maybe a sort of simple basis of data science would be helpful, or some backing in math, as Marcelo said. But there are many use cases that's not needed at all, in particular with the way that duality in specific is used. It's a great question. Thanks for asking.
Okay, I think this is going to be a good place for us to wrap up. For those who submitted questions that didn't get answered, we'll follow up with responses via email. If you would like to meet with a member of our solutions team for a one-to-one demo or to discuss your data needs, there should be a link on the screen. Marcelo, can you go on to the next slide? There you go. So please go to the link on the screen, and I'll also follow up later today with an email sending you this link and other useful links to get more information. So thanks for participating in our webinar series. We hope to see you again soon. Thank you, Marcelo. Thank you, Ronen.
Thank you.
Thank you.